In this video, we are going to talk about invertibility and isomorphic vector spaces. This is our overview slide, which we'll spend about 5 minutes going over before we go over each of these topics in more detail and with more examples. We will start by identifying an invertible linear map. So a linear map T from V to W is called invertible if there exists a map S going the other direction from W to V, such that S times T, or S composed of T, equals the identity map on V, and T times S equals the identity map on W. And this is the drawing that goes with this idea. In this picture, we have our set V, which includes an element X, and a set W. So our T operates on mapping from V to W, so it can operate on this element, this vector X, and map it to T of X in W. Now, in W, we have a map S that goes from W to V, and when we take S and operate on T of X, we get right back to X in V. And this way, this S of T of X is the identity because it takes any vector X and it returns back the vector X. We have this definition: a linear map satisfying ST equals the identity and TS equals the identity is called an inverse of T and is notated T inverse with this -1 exponent. We have the theorem that an invertible linear map has a unique inverse. So S in this case would be unique for T. And then this next theorem: a linear map is invertible if and only if it is injective and surjective. So this is our important theorem. So invertible, it needs to be injective and surjective. And an example of a function that, or a linear map that is not invertible, is the backward shift map from f infinity to f infinity. And if you recall, what f infinity does is it takes an infinite sequence of numbers and then gets rid of the first element. So T of x1, x2, x3 up to, and then it just goes on infinitely long, the sequence of numbers, is equal to x2, x3, and then it continues. But it's getting rid of this x1 coordinate. And you can see T is not injective. It's not 1-to-1 because T of x1, x2, x3 is equal to T of y1. So these first two elements can be not equal, but once you pass them through T, they'll have the same result. So what you have are two different elements mapping to the same element, so it's no longer 1-to-1. But when you do have an invertible map, what you get are isomorphic vector spaces. So an isomorphism is an invertible linear map. So two vector spaces are called isomorphic if there is an isomorphism from one vector space to the other. And isomorphic means same shape. So an isomorphism is, in a sense, a relabeling of vectors V into vectors TV and W. And of course, the idea of an isomorphism, it's not just that you relabel. In other words, it's not that you have the same elements in V and W and you can just match them up 1-to-1 and onto. It's the fact that they have a same sort of structure, and that structure comes because you do have a linear map. So it's the combination of the linear map and this 1-to-1 onto-ness that give or make the two vector spaces essentially the same structure, just with a renaming of its elements. We have this next very powerful theorem, a little bit of a surprising theorem. Dimension shows whether vector spaces are isomorphic. So two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. So if you really think about it, what this means is any n-dimensional vector space is isomorphic to Rn and Fn. And really, this is really powerful because we're so used to working in Rn from vector calculus. So any vector space that is n-dimensional can be relabeled and made into Rn, or if you want to put in complex numbers, Fn. From our previous video about linear maps, we talked about this notation, the script L of VW. This is the set of linear maps from V to W, And what we found is the set of linear maps from V to W is in itself a vector space. So here, the vectors are transformations from V to W. So remember, that's what this L of VW is. And we have this theorem that the set of linear transformations from V to W, and here Fmn, that's the set of M by N matrices, are isomorphic. So suppose V1, V2 up to Vn is a basis of V, and W1, W2 up to Wm is a basis for W, then M is an isomorphism between the space of linear maps and the matrices, M by N matrices. This is the picture that kind of helps me sort all of this out. So here, again, we have our set of linear transformation, or our space of linear transformations that go from V to W. So I have several transformations, T1, T2, T3. They're all different transformations that map V to W. Over here, I have all of my M by N matrix. I probably should have called this matrix like A1 and this matrix A2, just to emphasize that they're different matrices. So I have a bunch of M by N matrices over here. And this set of matrices is also a vector space. I think we proved that way long time ago when we were talking about vector spaces. So here, we're saying that there's this transformation M that makes this set of linear transformations isomorphic to the set of matrices. In other words, you can associate with each transformation a matrice. And then the other thing is, well, how do we get this matrix? That came from, this is kind of a review from a previous video when we talked about matrices of linear transformation. So the matrix of a linear map, M of T, suppose T is a linear map. We have V1, V2 to Vn. It's a basis of V, W1, W2, Wm is basis for W. Then the matrix of T, with respect to the bases, is the M by N matrix, M of T, whose entries A sub jk are defined by this formula here. So T of Vk is equal to A1k W1 plus A2k W2 plus AMk Wm. So we have examples of this in a previous video. We'll also do one or two examples in this video. So this might seem kind of strange because now you have a mapping that takes mappings, or a mapping of mappings to matrices. It seems very meta, but I will tell you, you want to get comfortable with this idea because we're going to do mappings of mappings in the next 2 or 3 videos. Finally, we have this theorem that says the dimension of the space of linear maps from V to W is equal dimension of V times dimension of W, when V and W are finite dimensional. That wraps up our overview, so we're going to come back up here and start again, look at invertible linear maps in more detail. We'll start again with the definition of an invertible linear map. So a linear map, T, from V to W is called invertible if there exists a linear map S going the other direction from W to V, such that ST equals the identity map on V and TS equals the identity map on W. So the idea here is we have our set V and our set W. We have an element X in the set V. The linear map T then will take this X vector and map it to some vector T of X in the space W. Now if T is invertible, there's going to be another map S that goes from W to V, this is S, and if we plug in T of X into S, it's going to bring us back to X. So it's the idea like of inverse, like when you have the inverse of addition is subtraction, the inverse of multiplication is division, because that's kind of how you undo the operation. So the inverse, this S, sort of undoes what T of X did so that you're back to where you started. And if there's an inverse, then the opposite is true. So if S is the inverse of T, then T will be the inverse of X. So in other words, if you start with S, you transition over here to some element in V. When you take T on whatever element S mapped to, you'll end back to the same element you started with in W. In this way, S composed of T, or S times T, is equal to the identity matrix, because the identity matrix, if we operate on X, we just get back our vector X. And that's essentially the same thing as what happens as if we operate first by t and then by s. We get back our original x. And t of s is also equal to the identity matrix. And then we have this notation, since this kind of looks like multiplication, it's the same sort of inverse we have with the negative exponent. So s is equal to t to the negative 1, and t is equal to s to the negative 1. But we usually don't read this as an exponent. We read it as s equals t inverse and t equals s inverse. We have this theorem that an invertible linear map has a unique inverse. In other words, there's not two different inverses. There's only one inverse. And to prove this, we're going to use contradiction. We're going to suppose that t has two inverses. S1 is equal to t inverse and S2 is equal to t inverse. And what we will do is we will show it's necessary that S1 is equal to S2 if they are both truly inverses. Since we know S1 is the inverse of t, that means S1 of t is equal to t S1, which is equal to the identity matrix. That's just the definition of what it is to be the inverse. Similarly, for S2, since it is also an inverse of t, S2 times t is going to equal to 2 times S2, it's equal to I. And I'm just going to note these two statements is just by definition of inverse. So I'm going to start with S1 equals S1I. And the reason why I do this is I want a statement relating S1 and S2, but they're not really related, but they do have this t in common, and they do have I in common. So I'm going to kind of force an I in here, but that's okay. I can do that because the I is just the identity. So I'll get back my S1. But now again, the whole point of putting in this I is I could introduce S2. So now I have a statement about S1 equaling S1 times, now my I can use this TS2, which then means I can regroup these. Remember, multiplication of matrices is associative. So I can group S1T. S1T is equal to I, so now I have IS2. And finally, I have S2 here, so I have S1 is equal to S2. And hence I have shown that an invertible linear map has a unique inverse. My next theorem says a linear map is invertible if and only if it is injective and surjective. Because of this if and only if, I have two parts to this proof. These two arrows in parentheses remind me which direction I'm going. When I'm going in the forward direction, I'm going to assume this first part invertible, and then I'm going to show that implies, that's the forward direction, it's injective and surjective. So that's the forward direction. The backwards direction takes this part here and says if it's injective and surjective, then the implication going the other way is that it's invertible. Again, injective and surjective implies invertible. And we are going to start with the forward direction. So in the forward direction, we want to show if it's invertible, that implies injective and surjective. We're going to start with a transformation, a linear transformation t from v to w. We're going to let t be invertible. Again, that's part of our given. So if it's invertible, there's an inverse. We'll call it t inverse. So t times t inverse is equal to t inverse times t, which is equal to the identity matrix. We want to show injective and surjective, so that's going to be two parts. First, to show something is injective, we need to show if t times the vector u is equal to t times the vector v, that means u must be necessarily equal to v. That's just the definition of one-to-one. And so we're going to start with t of u equals t of v, and what we want to show that u must necessarily equal to v. So when I look at this equation, I want to get u is equal to v. So I want to get rid of these t's. And I can do that by multiplying both the left and the right-hand side of the equation by t inverse. And you do want to be careful because matrix multiplication is not commutative. I do multiply both sides of the equation on the left by t inverse. So this is t inverse t, tu, and again on the left is t inverse t and v. And now, because matrix multiplication is associative, I can associate my t inverse with t, and I get the identity matrix, which leaves me with u equals v, and therefore t is injective. Next, to show surjective, I'm going to take W and say that's an arbitrary vector from the space W, and we will need to show there exists a vector V in the space V such that T of V is equal to W. And what I'm going to do is I'm going to say W is my arbitrary vector taken from the space W, and I'm going to consider TT inverse W. And you note TT inverse is definitely a vector because TT inverse is just the identity matrix. So I can do this, and this is well defined. And now what I can do is I can say, well, if I just look at this much of it, this T inverse of W, this is actually a vector in V, because remember, T goes from V to W, that means T inverse goes from W to V. So this is a vector in V, which means I have found a vector in V that when you put it into T will map to W, and therefore T is surjective, and I have shown that a linear map that is invertible means it is injective and surjective. Now that I have proven the forward direction, I want to prove the opposite direction. I want to show if we have something that's injective and surjective, that implies our mapping is invertible. And I'm going to start by saying let T be a linear map from V to W. T is injective, which means T of U equals T of V implies U equals V, and T is surjective, meaning for all vectors W in the space W, there exists a vector V in the space V such that T of V is equal to W. To show now that T is invertible, we want to find an S such that S times T and T times S is equal to the identity. Since T is surjective, for every vector W in the space W, there's a corresponding vector V in the space V such that T of V equals W. And because T is injective, this vector V over here such that T of V equals W is unique. And here I have my little drawing. I have our vector space V, our vector space W. So our T will match up with this W exactly one vector V, and it's exactly one because it's injective, it's 1 to 1. And it also, we're guaranteed that something maps to it because it's surjective. So there's no possibility of nothing mapping to it. So it looks like this, exactly like this. And what we're going to do is define our inverse S on W to map back to this V, the same V. So we're just going to say S then is going to look like this. For every T that maps a V to a W, we're just going to define S as mapping back to the V. So this is defined S of W equals V, where T of V is equal to our W vector. And we know this S mapping is defined because W is onto, and it's well defined because V is 1 to 1. So what we have is T of SW now is equal to T of V, which is equal to W. So in other words, TS of W is equal to W, and ST of V is equal to SW now, which is equal to V. So in other words, ST of V is equal to V. In other words, TS together as a transformation takes a vector W and it gives you back your W. So TS is the identity in our W vector space. Our ST over here takes a vector V and gives us back our vector V. So ST is our identity in the V vector space. And therefore, we've concluded our proof that our injective and surjective linear map gives us an invertible linear map. I have our two definitions here, first of invertible linear maps and definition of an inverse, as well as our two theorems. The first, that an invertible linear map has a unique inverse, and second, a linear map is invertible if and only if it is injective and surjective. From here, I'm going to give you some examples of linear maps that are not invertible. Our first example is T is a linear map. It maps the polynomial space with real coefficients to the polynomial space with real coefficients, and it looks like this. T takes a polynomial p of x and it multiplies it by x squared. Now, this is an example of something that is not invertible, so it either fails the test of being injective or it fails the test of being surjective. Well, certainly if you're multiplying polynomials by x squared, that means T will map to the space of polynomials that are of degree 2 or more. So in other words, T is not surjective because P1 of x, let's just take it equal to 1, or we could take P2 of x, which is equal to x, is not in the range, and therefore by our theorem, it's not surjective and therefore not invertible. Our next example is one we covered in our overview. So that's the backward shift linear map from f infinity to an f infinity. And remember, f infinity is just a sequence of an infinite number of complex or real numbers. So t takes this infinite sequence, x1, x2, x3 up to infinity. And what it does is it backward shifts. So it shifts everything over and it gets rid of the first element or first coordinate. So we're left with x2, x3, etc. So the thing about this is not one-to-one because there are multiple vectors that can map to the same result. So just looking at our theorem, a linear map is invertible if and only if it is injective and surjective, but here I'm telling you it is not injective because these two sequences, x1, x2, x3 on to infinity, y1, x2, x3 onto infinity map to the same vector then. They're both going to map to x2, x3 up to infinity, even though x1 does not equal to y1. So for example, t of 0, 0, 0 into infinity is equal to t of 1, 0, 0 onto infinity because what the backward shift will do is get rid of the first element. And so we're left with 0, 0, 0 onto infinity. Now that we've talked about invertible linear maps, inverses that are unique, as well as this theorem that says invertibility is equivalent to being injective and surjective, we're ready to talk about isomorphic vector spaces. First, an isomorphism is an invertible linear map. So these invertible linear maps give rise to isomorphisms, and two vector spaces are called isomorphic if there is an isomorphism from one vector space to another. And isomorphic means same shape. So an isomorphism is essentially a relabeling of vectors of V in the vector space V to vectors TV in the vector space W. That is, making a little bit of space here, we have our vector space V, our vector space W, when we have an isomorphism T that takes X to T of X and W, and then we have its inverse that maps it back to X. Essentially what we're saying is X and T of X are sort of equivalent or analogous in each of their vector space. They sort of play the same role. And even stronger, because T is linear, that's the other half. It's not just this fact that they're one-to-one and onto, but because T is linear, when you map V1 to W1 and you map V2 to W2, then V1 plus V2, remember, because V is a vector space, V1 plus V2 needs to be in the vector space. So that resulting vector of adding these two vectors together, which is V1 plus V2, is going to map to W1 plus W2. Remember, T is linear, so T of V1 plus T of V2 is equal to T of V1 plus T of V2 is equal to W1 plus W2. This sort of looks like T of W1, but that's actually a W1 with the vector line over it. So when we say same shape, that means the structure that we have from vector addition and scalar multiplication is preserved, so that the different vectors in each vector space, when they're matched up and their addition and scalar multiplications are matched up so that they're preserved one-to-one onto. And again, an isomorphism is equivalent to being invertible. An invertible is equivalent to being one-to-one and onto. This next theorem is kind of surprising but extremely powerful, and you'll probably end up remembering just because it's so powerful. Dimension shows whether vector spaces are isomorphic. So two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. And before we do the proof, I want to remind you why this is such a powerful theorem. It says that any n-dimensional vector space is isomorphic to Rn and Fn because they have the same dimension. And that's very powerful because you can have a totally new vector space that's foreign or new to you, but because you know it's n-dimensional, you know that there's some sort of isomorphic mapping to Rn, and once you get that mapping, you can just work in Rn. So now we're ready to do the proof, and again, because of this if and only if, we have a forward direction and a backwards direction. The forward direction assumes that we have two finite dimensional vector spaces that are isomorphic, and we want to show they have the same dimension. So isomorphic implies same dimension. Again, also they're finite dimensional. Second, the other direction is we start with they have the same dimension. We want to show that they are isomorphic. We are going to start with the forward direction, that isomorphic implies the same dimension. So we start with our linear map T from V to W, and T is an isomorphism from V to W. So because it's an isomorphism, we know that it is one-to-one and onto, and it is invertible. From this theorem, when we were talking about null spaces, that says injectivity is equivalent to the null space equaling 0. That is, if T is a linear map from V and W, then T is injective if and only if the null space of T is equal to 0. Well, here, since T is one-to-one or injective, that means the null space of T is equal to 0. Also, we know T is onto, that means the range of T is equal to all of W. Now, by the fundamental theorem of linear maps, and this is from our video about linear mappings, suppose V is finite dimensional and T is in the set of linear maps from V to W, then the range of T is finite dimensional, and the dimension of V is equal to dimension null of T plus dimension range of T. So applying this theorem over here, we have dimension of V is equal to dimension null of T plus dimension range of T. And in this case, dimension null of T, since the nullity is equal to the 0 vector, is equal to 0. So this means the dimension of V is equal to dimension of W. And just a reminder, a dimension of a single vector is 1. The dimension of the 0 vector, which is just a point, right? So if you think of the x, y coordinate, it's just a single point. So the dimension of that single point is 0. So that's our proof in the forward direction, that if we have isomorphic vector spaces, then their dimensions are equal. So this forward direction is proven. We're going to prove the opposite direction, which is the same dimension implies isomorphic. So we're going to start off with dimension of V equals dimension of W. And again, we're finite dimensional. So we're going to let V1, V2 up to Vn be a basis for V, and W1, W2 up to Wn. And again, both of these have dimension equal to n now, be a basis for W. Now we're going to propose our linear map T that we will claim is isomorphic. And what T does then is it takes a vector V. And because V1, V2 up to Vn is a basis, V can be written as a linear combination of its basis vectors. So V is equal to C1 V1 plus C2 V2 up to Cn Vn. The transformation we will propose then is to take these constants C1, C2 up to Cn and multiply them times the corresponding vectors W1, W2, Wn. So our transformation becomes C1 W1 plus C2 W2 up to Cn Wn. So this is the transformation we're going to propose as being our isomorphism. And T is well defined because, as we mentioned, V can be written as a linear combination of its basis vectors of V. And also C1, W1 up to Cn, Wn is defined since the W1, W2 up to Wn is a basis of W and spans our vector space W. And this last statement implies that T is surjective because W1, W2 up to Wn spans W. And now, remember we want an isomorphism. We have surjective, so now we need injective. Now when we consider the null of T, the null space of T, let's come back up here. We're looking to all our vectors, they're linear combinations of W1, W2 up to Wn. When we look for the null, we're going to set this equal to 0. So actually let me do this in blue because I'm kind of adding it here for this part of our thing. So when we set this equal to 0, because we want to look for the nullity, what we know is, well, W1, W2, Wn, they're linearly independent because, to be a basis, you have to be linearly independent, which means this homogeneous equation has only the trivial solution, which means the null of T is equal to 0. It's only the trivial solution, and I should put the 0 because it's really the 0 vector. And in our previous video when we talked about injective and surjective mappings, we said that the nullity equal to 0 is equivalent to being injective. Let me look for that theorem for you. It's this theorem here. Injectivity is equivalent to the null space equals 0. And now that we have T is injective, and earlier somewhere up here we said that T was surjective, that means that we have an isomorphism, because that's the definition of an isomorphism, and V and W are isomorphic. And we've proven our theorem. And I feel like one of the most surprising and powerful consequences of this theorem is that any n-dimensional vector space is isomorphic to Rn and Fn. And I like to think of Rn because that's the one I'm really familiar with, having worked with it in vector calculus and all the time now in linear algebra. Now that we've talked about isomorphisms, we're ready to talk about this last theorem here. I moved my definition of isomorphic vector spaces here for your reference, and I have our theorem. So the space of linear mappings from V to W and the space of matrices that are M by N are isomorphic. This is our theorem. So suppose V1, V2 up to Vn is a basis of V, and W1, W2 up to Wm is a basis of W, then M, this capital M, is an isomorphism between the space of linear maps and the space of matrices. Before I give you an explanation of this, I do need to give you a couple of notation notes. So recall that f of mn for positive n integers, that represents the set of all m by n matrices with entries in the field or complex or real numbers. And the dimension of f of mn is equal to m times n. The other definition I want to remind you of is the matrix of a linear map. So M of T. So if T is a linear map from V to W, V1, V2 up to Vn is a basis for V, and W1, W2 up to Wm is a basis for W, then the matrix of T with respect to these bases is the M by N matrix given by M of T, whose entries A sub jk are defined by T of Vk is equal to A1k W1 plus A2k W2 up to AMk Wm. So we've seen this definition before when we talked about matrices, but I wanted to remind you what this looks like, and I will show you the example of this in this video. But I want to first go back to this theorem and make sure we understand what we're saying. So we have the space of linear maps. So here, L of VW, that's the set of all transformations that go from V to W. So here's one linear map from V to W, here's another linear map from V to W, and here's a third linear map from V to W. So remember from our previous video when we talked about linear maps, this set of linear maps from V to W is a vector space. Now what we have is the set of all M by N matrices. So, maybe I should have called this A1 because this is my first M by N matrix. This should be A2, my second M by N matrix. This is A3, a third M by N matrix. And there's, an infinite set of these matrices. And let's look at our theorem So we have the set of linear transformations, we have the set of our M by N matrices, and we're saying M, that's this matrix here, is an isomorphism between our set of linear operations and our matrices. So I'm just going to write that here. This M, this matrix here, well actually it's not the matrix, it's the mapping that takes this linear map and produces a matrix then, is an isomorphism between our linear maps and our set of all matrices. And it's kind of funny because in our previous video when we were talking about matrices, we talked about M of t as a matrix, not as a mapping. But I'm going to say it's sort of like the analogy is when we talk in algebra at f of x. Sometimes we're talking about f of x as a mapping from, I don't know, some real number to another real number. So we can think of f of x as a mapping, but we can also think of f of x as the value it produces. So like, for example, f of 2 might produce 5, right? Or we could say f of x is equal to x squared plus 1 or something, in which case sometimes we're talking about it as a function, and sometimes we're talking about the actual number it produces. In the same way here, sometimes when we look at M, we're talking about the mapping from the association of a linear mapping to a matrix, and sometimes we're just talking about the matrix itself that results from after you plug in a transformation. And this mapping is how we get that is exactly the same technique or the same formula here that we used in our previous video when we talked about matrices and linear maps, and we're going to do an example later in this video. But first I want to prove this theorem here. I've cleared up some space, but I kept my theorem here. So the space of linear maps from V to W and the space of M by N matrix are isomorphic, and I put that little drawing over here for your reference. Now I probably should put this, I'm going to get rid of this definition over here. This is probably more important, our definition of our matrix of a linear map. So this that we had looked at in our previous video and we're going to do an example of, we know from our previous video that M is linear. So what we need to show for M to be an isomorphism is we need to show M is injective and M is surjective. And we're going to start with M is injective. So we're going to let V1, V2 up to Vn be a basis for V, and we're going to try to prove injectivity by showing the null space equals 0. So we're going to consider the null space where our mapping takes our transformation and maps it to the 0 vector from some linear transformation going from V to W. So kind of looking at the picture, we have this, we have V to W, we have some transformation T, and when we take the mapping of this transformation, it's equivalent to this 0 matrix. So now to go back and look at what this transformation looks like, we know what we want our matrix to look like. It's the 0 vector. But let's look at what happens to our transformation using this definition here of how we get M of t. So we said that we have V1, V2 up to Vn, that's our basis for V. W1, W2 up to Wn is our basis for W. The matrix of T, that's what we got over here, which is all 0, with respect to these bases, is the matrix whose entries A sub jk are defined by this. So let's take a look. What does T of V1 look like? So I have this written here, and I'm going to read it off from here. Well, that's going to equal to A sub, in this case, our K over here is equal to 1 because we're looking at T of V1. So we have A sub 1, 1 times W1 plus A sub 2, 1 times W2 all the way up to A sub, and I should put it M, M1 WM. We can also write this for T of V2. So over here, our K now is equal to 2. So T of V2 is going to be A sub 1, 2 W1 plus A sub 2, 2 W2 all the way up to A sub M2 WM. And we can keep doing this using this formula. But what does that tell us about our transformations? Well, T of V1 is equal to A sub 1, 1, W1. A sub 1, 1 is 0. In fact, all of these entries are 0, which means our T of V for every basis vector are all equal to 0. T of V n. So I'm just going to write this here, then T of Vk for our basis vector equals 0 for k equals 0, 1, all the way to n. And then because any vector in V can be written as a linear combination of our basis vector, all of our vectors are going to be transformed to the 0 vector. That is, for all vectors V in the vector space V, V can be written as a linear combination of our basis vectors. So when we take our transform on V, we take the transform then on this linear combination of vectors. Because it's linear, it all works out to be equal to 0. That means the null space is equal to uniquely 0. That is, when we had this mapping from our transformation, when we mapped it to the 0 matrix, that must have meant that all of our vectors were equal to 0. So the null space is uniquely 0, or only 0, which means that our transformation M is injective. Now that we've proven injectivity, we need to prove that M is surjective. But this is easy. So essentially what we want to show is that for any matrix A that's M by N, we want to find a corresponding transformation. But we have this definition right here, how we got M, but we can use it backwards. Once we have a matrix A, we can define our transformation. And essentially what ends up happening is our transformation simply becomes our matrix A multiplied by our vector W. So again, we're going to define T as our linear transformation using this formula here, and I just kind of used the summation notation. But you can convince yourself this is really the same as this formula here. So I have T of V sub k is equal to the summation j equals 1 to m, a sub jk times wj. And what this formula here is for is this is how you do matrix multiplication of the matrix A times W, a vector W. So the transformation T is then the matrix multiplication. So given a matrix, we can devise a transformation, and therefore M of T equals A is surjective. This video has been very theoretic, and I am going to give you one more example, hopefully to kind of tie all of these pieces together. But before we do that, I'll state one last theorem, which I will state without proof. So the dimension of the space of linear maps from V to W is equal to the dimension of V times the dimension of W. And this works when V and W are finite dimensional. Be careful, because if V and W are not finite dimensional, if they're infinite, then you cannot use this theorem. And for my last example, to hopefully tie a lot of this stuff together, looking at this theorem, the space of linear maps from V to W and the space of M by N matrix are isomorphic, kind of this picture here. I'm going to bring back an example that we had when we talked about matrices of transformations. And the problem was, given this transformation F, and actually I don't like using F as the name of a transformation because it looks too much like fields, like the field F. Okay, so the transformation T of xy, so it's going from R2, or maybe it's F2, to R3, or maybe F3. So T of xy maps to x plus 3y. The second coordinate is 2x plus 5y, and the last coordinate, or third coordinate, is 7x plus 9y. And the problem in our previous video when we talked about matrices of linear transformations was to figure out the matrix that represented this transformation, this M of T. And if you recall, what we said is once you know how a transformation transforms a basis, you know how it transforms all the other vectors. So the first thing we did was we got a basis for this F2, which is 1, 0, 0, 1, and a basis for F3, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. We applied our transformation to our first basis vector, 1, 0, and we get the vector 1, 2, 7. And in our previous video, I showed you that this also can be written as a linear combination of our bases in our new space, F3. So it's 1 times our first basis vector, 2 times our second basis vector, and 7 times our last basis vector. But this is the transformation here, so this is probably what we're going to need for this video. Then we transformed our second basis vector, which is 0, 1. So t of 0, 1 gave us 3, 5, 9. Again, we can write it as a linear combination of our basis vector and our new space. Now, because we know how this transformation performs on our two basis vectors, we know how the transformation performs on any vector v in our vector space capital V, because any vector v can be written as a linear combination of our two basis vectors, which led us then to our matrix of our transformation was equal to our first basis vector transformed, which is 1, 2, 7, and our second basis vector transformed, which is 3, 5, 9. This should all be kind of review for you. So I shrank all this down so I could enlarge this here. And this is where we want to tie all these ideas into our theorem so we understand better what's going on. But our theorem is about the space of linear maps being isomorphic to the space of matrices, m by n matrices. So over here we have a transformation. It's in the space of linear maps from F2 to F3. So we have our vector space V, which is F2, our vector space W, which is F3, and T is one of the linear maps from F2 to F3. There's a whole bunch of other linear maps, but we're only talking about this one example, which is in this space here. Then over here, we have the space of matrices, and there's a whole bunch of matrices, but we're going to focus on this one matrix for now. So the matrice that we got, the 1, 2, 7, this 3, 5, 9, is in the space of matrices of 3 by 2 matrices. And what we're saying is that our mapping M of t will map this transformation T that we have defined here. This transformation T is going to be mapped to this matrix here. There are other linear maps, there are other matrices that M will map from this transformation to some other matrix. It'll map another transformation to some other matrix. And what this theorem is saying, that this mapping then is an isomorphism between these two spaces, the spaces of linear maps and the spaces of m by n matrices. And exactly what is this mapping? What is this isomorphism? It was given to us in our previous video when we talked about the matrix of a linear map, and it is exactly this mapping here. This kind of seems like a long way of saying that you can convert any transformation to a matrix, except I think understanding exactly what each parts of this theorem is talking about is important if you really want to work with this theorem. To review what we've covered in this video, we talked about invertibility and isomorphic vector space. We said that an invertible map is a linear map T from V to W if there is a linear map S from W to V such that S times T equals the identity map on V and T times S equals the identity map on W. And then we defined a linear map satisfying S of t equals I and T of S equals I in inverse of t, and is notated T inverse, or this T to the negative 1 power. We had a theorem that an invertible linear map has a unique inverse, and then this theorem which told us how we would know if we had an invertible map, which is a linear map is invertible if and only if it is injective and surjective. And we did this example in the main part of our video. The next thing we covered were isomorphic vector spaces. So an isomorphism is an invertible linear map. So two vector spaces are called isomorphic if there's an isomorphism from one vector space to another. And isomorphic means same shape. So an isomorphism is essentially a relabeling of vectors v, the vectors v in the vector space v, to tv in the vector space w. And because this is an isomorphism that is injective and surjective, and also because T is a linear map, that also means the structure that you have on your space is preserved. The structure you get from vector addition and scalar multiplication is preserved. Next, we have this theorem that dimension shows whether vector spaces are isomorphic. So two finite dimensional vector spaces over F are isomorphic if and only if they have the same dimension. And for me, the big takeaway that's surprising and very powerful is any n-dimensional vector space is isomorphic to Rn and Fn. And last, we have this theorem that the space of linear maps from V to W and the space of M by N matrices are isomorphic. So suppose V1, V2 up to Vn is a basis of V, and W1, W2 up to Wm is a basis of W, then M is an isomorphism between the linear space of transformations and the set of matrices. And this matrix M was defined in our previous video when we talked about matrices of transformations. Finally, we have this theorem that the dimension of the space of linear maps from V to W is equal to dimension of V times dimension of W when V and W are finite dimensional. And that's it for this video. Thank you for watching.